なんでレコーディングするんだろうな。It is okay. So, just wait. Okay, I can see. Yes, today's topic is a Cryogen reaction, and yes, another reaction. That's the basic reaction. What is an Aldo reaction? We talked the last time there. So, and this also the similar, the same mechanism is the same, but the starting material difference. So, in here that. That's the use is ethyl acetate. This one is the starting material, and this one having the ester moiety here. Of course, this is the same as before. That's starting two more of the two equivalents of here. But it means that the starting only the same one molecule. And this one is yes. This is the use the basic the sodium alkoxide. This I use the etoxide. This is the very strong, the basic, and the finally generated the ket ester. This is the ket ester. That what difference is of course the newly CC bond was generated here. The newly CC bond here. Yes, this in and it's this called the ethyl acetate. Yes, this compound attack to another this compound. This one there. Yes, so it's almost similar at the same time like this. And the beta keto ester was the yes, so yes generated. This one the final compound. Yes, so difference of Aldo reaction is yes, the ester had the leaving group on the carbonyl carbon. It means that this the ester is a leaving group, so that the keto ester generated. So next slide, and this the mechanism here. Yes, several steps needed in the Cryogen reaction. At first, the first step is the formation of the nucleophilic inlet. Nucleophilic inlet. Yes, this one. This is the alcohol. This is the basic base. That takes the proton in here, and the electron is the back to the this is the behind this carbon, and the inlet in here, and this one the equilibrates the several form. This form equilibrates another form. That's the resonance stabilizes the inlet. This one the stabilizes this the formation. We cannot isolate each one. They are existing the both. Yes, this is the first step. Second step, yes the this one the nucleophilic attack. This one the here. This one attack to the another one more the same compound. Yes, another compound. This the attack to here. This one that so usually carbonyl carbon oxy is that the electron rich, and next to the electron deficiency. This is the plus. So this is always the look for the electrophile. So this is the nucleophilic attack here. This reaction easily. This is the negative charge. This is the positive charge. So that the reaction happen. And next, and this one is here. And that this is the electron here. This is the back to this is the carbon. And that this is the removed of the ester alkoxide, this one the etoxide, and this is the loss of the leaving group. It means that leaving group is here. Yes, etoxide group in here. This is the leaving group. This one here, the leaving group, and the beta keto ester was formed. Yeah, and the next step. This is also the strong the basic. This is strong basic reacted again. Yeah, this is the proton is alpha. This is the alpha position, the highly acidic place. Acid place easily remove the rest of the proton to give the proton to it's a strong the basic. And this is the reaction number 4. Yes, and move the reason rate, the stabilized end rate here again. And this one is that takes and this one is next to the aqueous acid solution, aqueous acid. This one is protonated again here. This is the takes the proton in here, and this is the beta ketoester generated. Yes, this one is the beta ketoester was reformed. This is the mainly reaction mechanism is a Cryogen reaction. Yeah. That's the important starting with a strong alkoxytic base needed. And removing group is that ester. And yes, finally this is they remove the etoxide alcohol. Etoxide is the strong base that takes the proton again. But this one, the reform the beta ketoester. Okay, this one next. Okay, this is also the explanation of the mechanism in the last page. And yes, so yeah, this one explained it again the how to this the reaction. This the reaction important is the first nucleophilic substitution. Yes, nucleophilic and the nucleophilic. In this case of this the reaction is inerate, and this is the leaving group is that alkoxide, etoxide is a leaving group here, leaving group, and the etoxide the here, yes, lost the leaving group in the here, yes, and yes, this one is the formed the beta ketoester formed. Yeah, they didn't. Yes, in here that they didn't mention about that. The removing the proton from the alpha proton by the alkoxide, but yes, that's probably but the result is the same. The beta ketoester was reformed. And next, and this one is the how to. Yeah, this is also a small example. Yes, small example, very easy example that yes, we want to try to explain. There, the starting material. This is here. Yes, here. This is the alpha proton in here. Alpha proton here. Yes, this is the alpha. This is the proton is the most acidic proton. This is the basic. Is that last time you used the etoxide. This is the metoxide, the basic. And finally, that's the aqueous solution, aqueous acid solution. So this is the Cryogen reaction. Those are the first three, and this is the alpha position. Alpha. This is the position is sorry, here it's the deprotonation, and here sorry, deprotonation. Then here. Yes, deprotonation, and this one is attached to the another is the compound, and here this compound is generated in the middle, and this one is also the electron rich in here. This is the electron in the back this carbon, and this one is removed. Yes, this metoxide alkoxide is the strong basic. This is the base. This is the basic. The base to take the one more proton in here. And this one is the minus charge, and this one is the aqueous solution. This is the proton, take the proton here, and reformed, and this compound, the beta ketoester. Yeah, this is the Cryogen reaction. Yes, very simple reaction, but very useful reaction to make that new CC bond. Yeah. This is example for the beta keto ester. OCH3. This is the deprotonation occurred, and this is the basic you did. Yes. So, for example, etoxide or something, OET minus. This is the minus. This is a nucleophilic attack. Yes. O minus OCH3, and this is the benzene ring here, and this is the methyl ester here, and yes, this is the carbonyl of the proton back here. This is the removed, and this is alpha proton very activated because of that surrounded by the two carbonyl here, and this was the deprotonation occurred against by the basic, and this one removed here. This is the minus or take here and the negative. Aqueous solution and reform again this compound. Okay, this is the Cryogen reaction. The same as this compound again. This is very basic, and I guess everybody also solve that problem. Yes, please try by your hand moving, not seeing this one. It's very easy. When you writing that you can easily understand. So yeah. こうか。ここポジティブで。Okay, this is a Cryogen reaction. So it's starting in the using in this reaction starting use ester group when they use it. Yes, ester group is the good to leaving the group. And next also again the cross Cryogen product formed from the each pair of the compound. Okay. First, we think again with negative charge. This is the alpha position, and reacted this one. Yes, the nucleophilic attack, and yeah, So I don't write all of them, but this one the compound generated is formed. Yes, and next B the long chain the 4 C OH OET. Yeah, so B C C also here plus and COOET. It's okay now. Okay. This attacked here. Here, this is the change that to minus Cryogen reaction and here and D is also here like this. And like this compound. This is no alpha proton. This is only alpha proton here. This is reacted here. And here, so a little bit complicated. Okay. Depronation again. ちょっとこれ忘れてる。Okay. Yes, so yes, so yes, the same. There's a similar, the reaction mechanism. But please, yes, consider it against by yourself the Cryogen reaction. And next is also the one example. Avobenzone. Yes, this one is our target product, and how to synthesize this compound by using the Cryogen reaction. Yes, so yes, so the Cryogen reaction we already ran that. So yes, this one is both the keto ester and the Cryogen reaction here. And each we can understand we make this one. But at first I think that this is a break this bond. And this one, the methyl OET. Oh.で、ここがこうが、benzene here and here, and this is a deprotonation again. The leaving that this is the OET, etoxide moiety, and this next compound bond. Yes, I think that. Yes, of course. Of course, you may have the different reaction mechanism, but also the yes, probably right. The when you start the Cryogen reaction. Okay. The next is that the other useful Cryogen useful the variation of the cross to Cryogen reaction. So and yes, from now that that's the starting materials. They having the not only the ester but also the chloride. This one is one more ester, carbonate, and ethyl the chloromate. So the chloride is a more good leaving group, leaving group rather than ester. So this one is a very predominantly very useful tool to make the Cryogen reaction. Yes, the formation the N rate, that's the same as the pure formation N rate, and the nucleophilic addition to carbonyl group, and yes, same, and the N rate. Yes, I'm not sure this one. For example, N rate is that called nucleophilic attack here. And the next is the elimination of the leaving group. Elimination that before that we just talking about the etoxide, but in case of here that the chloride is also the matched better than the useful than etoxide because this is the strong the electron density is the stronger than in the etoxide. So that's the good leaving group is the chloride. And here the next is this one, the beta G ester here, the beta G ester. Yes, this is also in that good leaving group. Yes. So next, and this is the reaction mechanism, and this is the reaction mechanism. Yes, this is the starting material. And activated the alpha proton. That is the proton is removed, and it's called that inerate here. Inerate is usually inerate is starting in the Cryogen reaction. And the next the react is the G ester moiety here. This is also some adjusted. ETO-COOET. This reaction is nucleophilic attack here, and this is the proton electron move here. Yes, and the next O-E-T-O-D, and this is the electrons back here to make the carbonyl, and this is the removed here, and this compound is found, and ethyl malonate is found. Yes, this one also again that reacted again and aqueous solution. Yes, and reform this compound the same as before. And yes, this one that reaction mechanism is right down here, and this one is the deprotonation here. Yes, and the electrons back to place. This is the carbon again. This is the negative charge, and this one is attack the nucleophilic. This is the carbon. It's electron deficiency, and this is the minus, and this is the nucleophilic attack. 2 is the second is the nucleophilic attack, and this is the leaving group with the chloride good leaving group rather than the good reading, the better leaving group rather than the etoxide, so that the chloride is removed, and this one the beta keto ester was found. The chloride minus here. Yes, this is a very easy the following the steps. So in here we have to keep in mind the chloride is the better leaving group. Yes, rather than etoxide. Okay, next is draw the product to each reaction. Yes, please consider this is the reaction. Yeah. Draw screw-hexagon already this one the starting material. OET minus the protonation, the electron back here, and minus charge, and this one attack to the ester compound, the ester carbonyl. Yes. Next, thinking C2 still and chloride carbonyl ester and this OET oxide that take one proton here, and this one the negative charge, this one attacked here, nucleophilic attack, and what can compound the intermediate? So sorry, なんかロストだ。こう。で、this electron back to the make carbonyl, and the chloride, the atom is the leaving group. She was found there. Yes. And next is step is two step in the synthesis, the analogic ibuprofen is very painkiller. The condensation reaction, the whole bioactivation reaction, intermediates. Or yes, we think we should think that this is the intermediate, but the very we have to use that Cryogen reaction. And yes, to which one difference to focus on the which part of difference. Yes, so this one, the one more methyl group here. Yes, difference the one more methyl in here. Yes, but this was the methyl iodide used for the SN2 reaction used here. This is the heat, and this means the heat. Heat and the heat mean the heating, and yeah, this is the okay. This is the starting. This one. Okay, this is starting. This the yes, alkoxide is etoxide. Take the one proton here, the strong the base, and this one strong base usually in T in plus. PT. This one to take the proton here. And this compound minus. This is the reacted next compound, Aldo reaction. And this and T. Smooth spaced out. The same as before, the same as before, and this one is again the reacted with that in this etoxide is the probably this is this protein the very strong acidity. It's because that's the both ketone group are both ketone is attached to this the same carbon. This is the very strong acidic. This is the easily is the taken by this the etoxide. Yes, and that this one also. Negative, and this one next is reacted with the methyl iodide, and the methylation occurred in here. This is the negative, this is the positive charge, and so this is the methylated occurred in here. And here next is the acidic solution, and the hydrolysis, this is ester, so is a change that carboxylic acid, see this aqueous solution, and this one the next is the heated, yes, heat, and so next to heated, this is the carbonyl compound is that the sodium carbon dioxide here. Excuse me, just a moment. Yeah, I'm very sorry. These are yes, so carboxylic acid deprotonation, the carboxylation occurred. Yes, the heating, and this component ibuprofen is what's the reformed. So this is the reaction. This is important is the first reaction, the Cryogen reaction. Yes. So probably you also can do. It's not so difficult. Yes. So I want to move to the next reaction. But I'm drawing here that's the pre-storage by yourself. The doing by yourself is very helpful. You would understand that's all reaction. Yes. Next is Dickman reaction there, and 5 and 6 membered ring are formed in this reaction. Yeah, so and yes, this is the 1 and 6 diester. This is the 1, 2, 3, 4, 5, 6, 60 ester and one and 6 carbons, they have that ester. And redraw like this, writing here the 1, 2, 3, 4, 5, 6. And this is the same, yes, the same reaction, the same as Aldo reaction. Is the sodium hydroxide used, and here, so this is the alpha position. This is the attacked here, the nucleophilic attacked here. This is the 1, 2, 3, 4, 5 attacked here. So like this. A little bit difficult. Write down. Here, stop. Yes, same as, yes, same, the Cryogen reaction. Yes. Yes, next is that the 1, 7, the ester 1, 7. This is the 1, 2, 3, 4, 5, 6, 7. Yes, the ester here. And this is the alpha position. It's attacked here. Nucleophilic attack. It is the 6-member ring, which 1, 2, 3, 4, 6-member rings. Yes. And the new bond here, the new bond here. Yes, very easy, but it's very interesting to make the ring that they're using the the Cryogen reaction. This is the reaction mechanism, Dickmann reaction. Yeah. Yes, I say again, this is the alpha position activated because next to the carbonyl group. And here, this is the attack to the nucleophilic attack. This is the carbonyl electrophile. Because this is always the negative with the plus, and the negative is the move to the plus charge. And this one, the nucleophile attack, and the 6-member ring. 6-member ring to found. And this one is the same as before. This is the electronic here. This electron is the back here, and the make the carbonyl group here, and ester is the hydroxide is the leaving group. Leaved here. Loss of the leaving group, and the decast ester is found here. And this is the leave moved here. The leaving group. Yes, this one is the base, strong base. This is the take the 1 proton here, and this is the negative charge, and this is the ethanol is found to take the proton. So. Here, acid is here, and the get ester again. So this is the reform of the beta keto ester. This is the reaction, the mechanism here. Okay, next, same as before. This is the beta keto ester found. This is the Cryogen reaction, but difference is that they can make the 5 or the 6-membered ring. Yes, because this is the 1 molecule have the 2 ester in the same molecule. That's the 1 molecule. The molecule is having the 2 more ester in the molecule. So this is a Cryogen reaction occurred. It's called a Dickmann reaction. Yes. Yes, this one also the example is the one synthesis, the prostaglandins, the PGA, the main kind of the prostaglandin is generated in our bodies as the controlling the blood pressure. That was the many important important to work the functions of the prostaglandin species. This is also the key. This is the synthesis technology. This is also the key step, a Dickman reaction. So Dickman reaction. So we have to think. This base means that so OH, OET minus or and methoxide here. This is set the basic base here. Soそれをメチルだ。メチル。ここか。で、こう。They make the carbonate here. There are several steps, and here the deprotonation and the double bond attached here. This is the key step. Is to make the 5-membered ring here. Okay, and next is that what the 2 keto ester will form as. When we use this material at the starting, that the 2 keto ester was formed. So we have to what type of the keto ester to found. Yes, we have to consider. Yes, so okay. So I want to reform this structure OET and here. The way is alpha proton, alpha here, and alpha proton here. So that the 2 possibilities activated alpha proton. If at first activated here, so this one is the attack to here. So yes, and yes, so here and here. Yes, this one is the carbonyl bond again. That's the ethoxide is a leaving group, and this compound was found. And next is okay. This protein is activated and deprotonated, and this is the carbon activated, the minus negative charge. If this compound attacked here, so maybe we can make this kind of structure. It's the same, the carbonyl bond here, ethoxide, the removed. And tissue. So to two compound was the founder. Yes, these ones looks similar, but actually the different. Yeah, so so yes, this one is the carbonyl. The next carbon next to the dimethyl. This is the carbon next to dimethyl. That the different compound. They are still more, but different compound. Yes, they are isomer. They are isomer. The different compound. Yes. So because this is the dimethyl, the bicynyl, the methyl attached to this is the carbon in here, so that the produced compound was different. So there is no selectivity, so that if we want to this compound again, we have to separate after the reaction. After reaction, it may not a good way. Yes, but the total yield decreases. But if we have this compound also, this compound is not important. We have to separate against after reaction mechanism. Of course, it's the better good way. We have to desire the starting material to get the desired compound. So that always the organic synthesizer side to try to find the good weight, the reasonable weight of the synthesized the compound. Yes, but this one is very uniquely interesting, very easy structured. But we are talking about the we didn't mention, or this is the mention, or the stereochemistry. Always the chemistry. Yes, the selectivity of that, the regional selectivity and the stereochemistry. This is the mention about stereochemistry. If we include if we consider the stereochemistry in each reaction, that's the makes the reaction much more complicated, but very interesting, important stereochemistry. Of course, okay. Next move is Michael reaction. Next is the Michael reaction. Michael reaction also very interesting structure. It's called the 1,4 addition. Yes, 1,4 addition. Okay. This is the two components of my. Of course, N rate. Yes, we use N rate. This one is acceptor. Is that the alpha, beta, unsaturated the carbonyl compound. This is the alpha. This is the alpha. This is the beta. Yeah, this is the unsaturated. This is the including the double bond here, double bond in here, and which is the counting this number. This is the 1, 2, giving the number of the carbon atoms, and the 3, 4. So that the Michael reaction is reacted in the carbon 4 and the carbon 1, and it says the 1,4 addition is also the beta position that attack to the N rate here. Okay, and yes, we want to see more. Yes, 2 electric sites and the carbon is the beta carbonyl. Okay, next. Yes, this is also resonance of the alpha beta unsaturated compound. So this one is always the carbon is the carbon oxygen minus, and next is the plus, minus, and the positive. And this one is that electron is the move to the carbonyl. This is also the one resonance. And the next is the double bond, and this is the one with the electron the move to this bond, and the electron here, and this is the plus charge, and this one is another, another resonance. So that these three compounds exist in the mixture, that we can isolate each one. We have to think this alpha beta, the unsaturated carbon compound, is that the hybrid like this. So because the electron is moving this carbon, and oxygen, and oxygen atom. This is the moving. So we we are writing like this, very yes, the conventionally, but the use always the electron is moving here, here. So we can write like this. We can write like this. So always is that attack to here. This one is a very easy attack areas, and it's called that's the 1-4 additional reaction. So 1, 2, 3, 4. This is the 4 position here. So it's called the Michael reaction. Michael reaction. So when you found the structure is alpha, beta, unsaturated moiety in the molecule, this is a very nucleophilic attack here, not here. Yes, so because this one is a reason to do one more double bond here. So this is easily attacked here. It's not okay. Next, next. Okay, resonance structure. Okay, yes, this one is the conjugate. Is usually nucleophilic is the negative. This is also N rate here. N rate. This is attacked here. This is the minus, the positive minus positive. So that this is the nucleophilic attack. That this is the carbon here, and moving the double bond here. Attack here, moving double bond next in here, and probably we can explain it again somewhere. So double bond move here and here. This carbonyl against makes the carbon bond, and this one is the move here, and this one is the yes, and take the proton from somewhere, and this one is that here that the newly bond is found here. So this is the Michael reaction. Yes, nucleophilic, that's the beta carbon. This is the alpha beta. So that's the beta carbon. Alpha beta. This is the example. Yes, this is also is reacted here, activated. So for example, CH3 CO CH2 alpha beta and CH minus. Yes, because this one the two carbonyl group attached here, they're highly activated here, this carbon, and this one here, beta attack here, not here. Yes, because this compound have the one more double bond the next to carbonyl. This is the very activated here, and yes, and this is the electron to the back to the carbonyl and make the carbonyl reform carbonyl, and this one in the compound here the new CC bond the found here the H2O. They take the proton from H2O, yes, water, and the new CC bond the found here. Okay, this is the beta position. It's the this is a Michael reaction or 1-4 and 1,4 addition. Yes, so yes, 1,4 addition to the 1,4 addition. This is they mentioned here. This is the main mention here. One is a carbonyl, oxygen is a carbonyl. This one is a negative charge. And this one is also attached to the proton. This is the 1 and the 4 is attached addition. So it means the 1,4 addition is the Michael reaction. And next, sorry, we had to explain this one. The second also the same reaction. Just a moment, so we can find the reaction mechanism here. This is the mechanism here. Yes, and yes, this one, the deprotonation. So sorry, this one, the protonation. Okay, this is the strong, the basic. Yes, this is it. And yes, this is the stable resonance stabilized N rate. This is the N rate. The attack to the same as this one. Yes, and this one attack the beta position, alpha beta. We are giving a number from the next to carbon to carbonyl, and look at the nucleophilic attack, and this one here. O minus, and here to here, and that this is also the make the carbonyl again and take the proton again. Okay. Yeah, this is the mechanism is written here. That we have to back the last page, the next before the forward, backward. And this was which the following the compound can serve as a Michael acceptor. Michael acceptor. Yes, Michael acceptor. What the acceptor mean that not enraged. Yes, a nucleophilic attack. Can say donor here. Acceptor is the enraged. Attacked here nucleophilic. This is the carbonyl. This is the alpha beta unsaturated. This compound, and next, and this one the alpha beta is not unsaturated. This one that alpha position only alpha. This one the alpha beta is found. This one double bond here, so that's the D and the A. This is the Michael acceptor. Yeah. Yes, beta in here, that's the NOH test attack to the beta carbon of the Michael acceptor. So that's the so that's the Michael reaction that need a double bond. Yes, alpha beta unsaturation structure. Okay, here. This is already mentioned. Always alpha beta unsaturated carbon. This is a good Michael accepted. Yes. Okay. This one, the last time I told here the deprotonation. Decarboxylation is by heating this example, decarboxylation, the heating. This is the Michael reaction, the product, and this compound. Yes. Here. Decarboxylated, yeah, decarboxylated, but the hydrolyzed here. Probably you can already know that, but I write again with the H2O, that's H plus 2H to minus here. No potassium. Yeah, and the heating with the easily and the decarboxylation occurred here, the CO2. Yeah. And finally, the 1,5, the decarbonyl compound was formed here. Yeah. Yeah, this is the very unique compound at the key step of inside the human sex hormone. Okay, next. Next. Okay, this is the exercise again. Program. What product the form the each pair of the compounds treated with the basic in yes no. Yes, we have to want to think again. Set to set 置いてYeah, this is activated because the both the carbonyl attached this carbon, and here, one beta attack in here. This is the beta alpha beta unsaturated here. That Michael reaction occurred, and so what compound are found? Okay. And B, C, sorry, C、これは A か、A、C とこうして、こうして、こう、CH、alpha, beta here. This is the position, the beta position, probably nucleophilic attacking here. What N rates they use that here? This also activated in that nitrile, attached to nitrile here. Yes, nitrile also activated with alpha carbon. And yes, this one nucleophilic attacked here. That's the Michael reaction. Next here, this one also alpha beta here. The CH2 Oh my gosh. So now, okay, getting tired. But this one, the simple reaction. Yes, the better. Yes, the beta carbon. The carbon is was attacked by the nucleophilic reaction by the enriched. Yes, yes. Please consider by yourself and please write that make the reaction mechanism by yourself, the handwriting. And next is example that the steroid synthesize. This is the Michael reaction. Use the Michael reaction. This is the very important step, the key step to making this moiety. Okay, this is also we want to think of this one again. Okay, this one. Okay, this one is the one proton here, and this is the alpha carbon is activated to double the carbon two ketone group in here. This is activated, but easily this is the deprotonation. And this is the negative. This is attacked here. The Michael reaction occurred. Yes. As the new bond, where the new bond, this one is attached to in here. This is several steps. But you may think about this one, but this one is not reacted. Yes, and this one also alpha position here. This is alpha position, but it's not reacted here. Not one reacted. This one is also the most acidic position in here because the two carbon ketone group attached to here. This is the most acidic position. This is also with alpha position. This is also with alpha position, but this one is very highly activated. Yes. The next not reacted here, but this one is reacted. Okay. Next, also the program, the starting material need to prepare to each compound by making a reaction. That's how to, yes, how to synthesize this compound A and B using the Michael reaction. Yes, we have to find out the both compound which enriched and which the Michael acceptor we can use to make this compound. So at first A, so this is the alpha position. This is the activated carbonyl ketone group. So, and this one is the carbonyl. This is the alpha beta position. If this is the cut here, yes, we can make the Michael reaction, the both compound. So we want to choose this kind of compound and this one. Yes, A. Yes, so yes, we can make that a strategy using the Michael reaction. This component is the same. Yes, the procedure. We want to think again. So yeah, this is the carbonyl group, alpha, beta, and here double bond. Double bond. This is a Michael reaction here. Double bond here. and acetone here, and this is the minus. Okay. Next is this is a target compound. B, the compound B. This is the Michael reaction. Yes, very interesting. But at first we are focused on the carbonyl group in the here, and that's the alpha beta position. And this one is the activated alpha proton. And this one is the alpha beta placed here. This is the alpha position. So probably this is the cutting here. We can make that the acceptor, Michael acceptor, and end rate here. Okay, next. So the Robinson annulation. Robinson annulation. Yes, this is the ring forming reaction of the combined Michael reaction and the intramolecular Aldo reaction. Yes, Robinson. At first, this reacted with the Michael reaction. First Michael reaction. This is the alpha beta. This is alpha beta unsaturated carbonyl group, and at first this one is the alpha position here. This one is the attacked here. Yes, and this moved here. And next is the Aldo reaction. It's again from here to here. The Aldo reaction here. Yeah. And so this one is the 3 bonds. The 3 bonds. 3 bonds mean that the one new CC bond and another the new CC bond and the pi double bond. They are sigma. Sigma is the single bond. Double bond. The sigma 1, 2 sigma, and one more double bond the same here. So it's composed of 3 bond found. 3 new carbon bond, 2 sigma, 1 pi bond. Pi bond means the double bond. Yes. This is called the Robinson annulation. It's a Nobel Prize. It's a very famous structure. It's very useful, very interesting. Okay, this is the reaction that happen in the intramolecular Michael reaction, Aldo reaction. Okay. Same basic as using here. Yes. This one also example. Negative charge. This is the Michael reaction, alpha, beta. Yes, beta position. The alpha proton attack the nucleophilic attack beta position. And this is the Aldo reaction. This is also alpha, the activated minus. And this is the ketone group, always the plus charge. So nucleophilic attack in the here. So make this is the single bond. And this one is sigma bond, and again the deprotonation. Yes, the dehydroxylation, elimination of the water. It's a double bond here. Alpha negative, alpha beta here. And this also is attacked here. So that's showing red here, the red thing here, new bond here. This is the Robinson annulation. Yes, this one is the six member ring. Because 6-member ring is a very much more stable. It's the other and and membered ring. So, and the 6-member ring with some dynamically it is stable. And next, this is the mechanism, the Robinson annulation. Yes, yes, the two parts. The first part, the Michael reaction, Michael addition, and next is that Aldo reaction. This is explained the Michael addition. Yes, at the first, and the acidic proton. Where is the acidic proton? Yes, this one is the acidic proton enrate because the key carbon ketone group attached here. This one is an enrate. Yes, enrate. So this one is the attack to the Michael reaction. Attack nucleophilic attack. This is the beta position. Yes. A nucleophilic attack under the newly CC bonds found here. Yes. Yeah, they are the same. Yeah, same thing. This is the proton. This is the electron. Yes, to take the protons from the water. Yes, and this one the saturated compound here. The 1,5 the decarbonyl compound. 1, 2, 3, 4, 5, 5. Yes, 1, 2. So 5, 5, 5. This is important. 5, 5. 1, 5. 1, 5 decarbonyl compound is found here. And this compound is reacted with Aldo reaction. This is the Aldo reaction. This is the alpha position. Is the proton takes the proton from oxide, the hydroxy oxide, and this is the protonate. This is the electron here, and this is the electron that nucleophilic attack. This is the carbonyl ketone, and this is the this one is takes the proton with the water, and this one is the beta hydroxycarbonyl compound here that we ran the last time, and this one is that, and again dehydrogenation occurred. Dehydrogenation means that this one the elimination of this group as water, and make the double bond here like this. Yeah, here this. This is the electron back here. This is the hydroxy group is removed, and this is the insert the double bond here. So finally, the new CC double bond in here. So this one is the Robinson annulation, the first 3, and the Michael addition occurred. And the next is that the Aldo reaction in the same molecule, and the inter-Aldo reaction, and this is the hydroxy group and removed, and to make the double bond here. And the finally it made the alpha beta unsaturated, and the 6-membered ring here. Newly formed ring. Yeah. Yes, the first read this one is Michael reaction, and the next the intramolecular Aldo reaction, and the N rate, Aldo reaction N rate, and the next nucleophilic attack, and the protonation, and the deprotonation, and the loss of the hydroxy group in the here, and the made the double bond here. This is the Robinson annulation. Yes, so this is explained the Robinson annulation. Robinson the product the annulation. This is starting goes to the material. Yes, this is also the beta and alpha beta unsaturated ketone group, and this one is also alpha position is activated needed because this one is attack to the attack to the alpha attack to the and the Michael reaction, and this one also is activated after that. Needs activated because the Aldo reaction occurred, and make this kind of the structure. Yes, I need the base needed because the alpha proton should be activated, the protonation. Yeah. So this is a very basic form. So that the scientists use that to make the single make the six-membered ring like this. So they may choose the starting material both this component and the Robinson annulation. Yes. Next, this is the mechanism. This is the example or the how to react to the both components under the Robinson annulation. Yes. So, for example, this one is as both are yes material, and yes, probably this is the carbonyl ketone group alpha beta, and this is the Michael addition acceptors. Yes. And this also is activated. Probably it's both ketone group that attached to the same carbon. Yes. So we can deduce this reaction occurred from here and the Michael reaction. Yes, okay. So that the newly bond in here and another is here. This is also the alpha position activated. This one is attacked to the here. Maybe we can speculate here. So we want to see that this is the reaction, and at first this is the most acidic the proton here. This is the acidic here. This is the Michael acceptor. And this is after Michael addition, the next intramolecular Aldo reaction. This is the alpha position activated. This one attached to here, attack the nucleophilic attacked here. And so this compound was found, and the protonation in the OH group, and this is the double bond here. So, and this one the double bond, newly double bond here, the newly bond here. So, yes, this one is this reaction. It's yes, Robinson annulation, that's Michael reaction, and the intermolecular Aldo reaction, and the elimination with OH group, and the newly double bond here. Okay, and this is the exercise and the program that draw the products with when each pair of the compound integrated in the basic condition in the Robinson annulation reaction. So we want to think solve that together. So here. Here and the activation here, and this one attack is there. So molecule reaction, and this one also then attack the in the multi-Aldo reaction is attacked here. So we can make the 6-membered ring. This here, the elimination, double bond. Here, there is A, B, C, or yes, here, and yeah, same that alpha, beta. This is the Michael reaction here, and this one is a Aldo reaction here. We can speculate. So 5 code. And the next B. Michael reaction, and elimination is water. Yes, and next, so I want to skip structure. Oh, so the excuse just a moment. Okay, next, okay, the final, almost the final. This is the how to synthesize the next Robinson using the Robinson annulation, and this one, yes, this looks very complicated. But at first, this is the same structure. The flip and the flipped structure, they are same structure, and change the direction, seeing the different direction, and cleaving the the double bond, cleavage the bond. So because this one the alpha position, beta position, and this one is the cut, probably the alpha and the Michael reaction. We make the insert this bond, and this one is a coming from the Aldo reaction. So we can choose the starting compound here, and this one, yes, and so this one is activate. So starting this one, we can make this compound. For example, this one, the called double bond here and here. So yes, and this one activated alpha position and attack here and here and here again. And so the protonation, the elimination also occurred. So we can make this the structure. So, yes, okay. But in case of this, this is also we can think that the Aldo we can the alpha beta activated. The same, no? Yeah, they are same, no? Same structure, just only they flip and this is also activated the same one, but this is not reaction is not occurred. Very this one is very unstable. This generates also the much more stable. This one is very less stable. So besides some dynamic rigid, it's this component is found. And yeah, sometimes we have to think that like this, we have to carefully choose the starting material. So yes, this is the final. So I want to solve this together. Yes, last one. Is cut here is here is alpha beta is double bond so that we can deduce we can make like this structure starting material. Yes, so this is the Michael reaction occurred. Oh, but this one is the several alpha, this one also the alpha proton. Is a little bit difficult to the selectivity. The several components found. Yes, I think so. And the next one here, cut. So we can reduce the here. The micro addition occurred, and this one the Aldo reaction. So I can make here wait now. Already this is activated, not here the activated, but this one is not occurred. The Aldo reaction is normally it's not occurred. Is it always activated? Yes, so that some dynamically is the generated only this compound. The hydroxylation occurred. This one. This also the thing we have to think. Okay. Yes, cut to here. And this is alpha, beta. This one here and here. Yes, and the duck here, the Aldo reaction, annulation, and But this one also happen in case of this, and here is both both alpha positioned here. If this is activated here, this one also is the bond attacked here. This is also cool. Yeah, this is my idea that this the one in the starting this is the post it's a starting material. So our reaction there probably I cannot how to control that this reaction. Yes, we can generate the both possibilities. After that we have to separate them now. Okay, thank you so much. The 24 this is the Aldo reaction. Yes, I want to complete my talk.
Yeah.
Thank you.
Thank you, Sensei, for a nice lecture and also a very detailed explanation about collation, condensation, Dickman condensation, and also Michael and Robinson annihilation. So yeah, now I think we are moving to the discussion session. We have several questions from the students in the chat box. I will read. The first question is coming from Muhammad Fakih Albi. Ohayo gozaimasu, Sensei.
Ohayo gozaimasu.
Dear Professor Yoshihito Oshiono, allow me to introduce myself. My name is Muhammad Fakih Albi from class A. I have one question. Why in Michael reaction the nucleophile endolate always attack the beta carbon, not the alpha carbon? Otsukare sama desu, Sensei.
I already told that's why is the reason. Yes, not reacted with the carbonyl position there because having the double bond. Yes.
Yeah.
Yes, resonance. Yes, resonance. There is another resonance. There is no reacted one to the Michael reaction.
Yeah, I think Prof. Siono has explained about the resonance. So making the beta position reactive as the acceptor. Okay. Can we move to the second question, Sensei?
Yes.
Yeah. So the second question is coming from Hidayat Nurul Mustafa. Thank you very much for your explanation. Very interesting. My name is Hidayat, and I have a question, but sorry if it's explained before. If it allows, is there any other base that can be used instead of sodium NaOH, sodium ethoxide in Claissen's condensation?
Oh, probably the stronger the base. If you need the strong base, the last time that I told that LDH, this is also the one possibility to, but there's a lot of the bases.
Yeah.
Yes, probably depend on your reaction there.
Yeah.
Not so difficult to find out other base.
Yes. Strong base, like LDA can be also used. Yes. Okay, another question is coming from Angelica Kurnia Herzandi. Good morning, Professor. My name is Angelica. I have several questions, but I'd like to say sorry if the question already explained before. First, Robinson annihilation, as explained, undergoes in base condition. What will happen if it is used in acid condition? Second question is, why is the dehydration favor at the end of Robinson annihilation? Is it okay if we don't do the dehydration, or will it affect something? Thanks in advance.
Yeah, acid is not. I've not seen the acid Why did he ask? Did she ask the acid condition? She needed something acid condition.
Yeah.
I don't know. Just asking. I don't know that. Probably the basic condition they needed is how to activate it, how to activate the enolate. Acid condition there. Aldo reaction that possible, but Robinson annulation is impossible. Yeah.
It's supposed to be a base, yeah. Use.
Yes, base. Yes, needed.
Yeah.
And Robinson annulation and loss of always provide this. This is elimination is the hydroxy group and elimination the hydroxy group, and they make the double bond. It is it should be occurred. Yes, because it's the next carbon is alpha proton. Alpha proton easily deprotonation, so that the alpha proton already deprotonation, so that easily it's inside the double bond. Elimination with the hydroxy group.
Yeah, sometimes it happens spontaneous, yeah.
Yes, spontaneously.
Yeah.
Yes.
Okay. Yeah, I think that's the question. And another question is coming from Arianti. Dear Professor Yoshihito, my name is Arianti. Thank you very much for your explanation. I have a question. Sorry if it is explained before. Other than OH in water and ethoxide ion in ethanol, are there any other reagent can be used to produce enolate from Robinson annulation? I think it's already been answered.
Yes, already. Yes, the basic needed. Yes.
Yeah, LDA can be used.
LDA can be, yes.
Yeah. Is there any other question from the student? You can ask also directly to Prof. Shiono, but first you need to raising hand first, yeah? Okay, April, you want to ask directly, yeah? To Prof. Shiono. Yeah, April, please.
Okay, thank you so much for the opportunity to that given to me so I can ask my question. And also I want to apologize because I can turn on my camera right now. Let me introduce myself. My name is Sabrianti Mulus and I'm from Class B. So in your explanation before, in another reaction, we can use a hydroxide base as a catalyst for the reaction. Our integration reaction, we can also use this base or we can use hydroxide base or not, and why? So the second question is, in the cross-reactivation reaction, you mentioned that chloride can perform as a good living group and form a beta kettle ester. So my question is, another good living group such as bromine can also form a beta kettle ester or not? Maybe that is the question for me. Thank you in advance, Professor.
Can you get the question?
Yeah. Yes, the first, the ethoxide or the methoxide is very strong, the basic, rather than OH group. Yeah, so that's very useful to use that make the enriched by using the ethoxide or the methoxide. They are very strong. So that we can imagine is that the ethanol or the methanol is how much the pH of this compound. It's not a very rare cases, the deprotonation of the ethanol of the methanol. It's a very rare cases existing the ethyl and ethoxide or the methoxide in the solution. They are always methanol and the ethanol. But the sodium methoxide, they are easily dissolved in the water and to produce the ethoxide methoxide that are the deprotonation is easily. That's because they are very not so strong with pH. Yes, and another living group is probably the several living groups that have that ethoxide and the chloride, the bromide, or the others. Maybe you can look for the good result of that textbook.
Yeah.
Yeah.
Okay. Thanks, Jose. Oh yes, Angelica. I don't think my second question answered. Yeah, I think Angelica, your previous question asking about dehydration, yeah, in Robinson annulation. I think it's already been answered. It's look like similar with the aldol, yeah, the aldol synthesis that also tends to give dehydration product. And yeah, Professor Shona has answered your question. Yeah, sometimes it happens like spontaneously during the reaction. Yeah, Angelica. Okay. Is there any other questions from the student? All right. I think yeah. I think there's no more question from the participants. So yeah, I will try to summarize for the lecture today to all of the students. So today, Prof. Siono has given a lecture about another carbonyl condensation, yeah, including Claisen reaction and also the intramolecular Claisen condensation that we call it as Dickman reaction, and also another type such as Michael condensation also has been explained. We can see another type using another acceptors, yeah, that differ with the other condensation. And also the last subtopic, Professor Siono has explained about Robinson annulation, that is a combination of Michael addition and also Aldo condensation. Yeah, I think that's what we have obtained from today's lecture. Prof. Siono also has give us some how to solve some kind of synthetic issue by solving some exercises today. So thank you once again, Siono Sensei, for today's lecture. And I believe it will increase the knowledge of all of our students. So yeah, but before we close, is it okay if we can take a picture together?
Yes, okay.
Yeah, not together,
yes.
Yeah, with all of us. So I hope the student can open the camera if it is possible. Student?
カメラ写真
Can you open the camera? Make the camera on. We will try to take a picture together with Professor Siono.
すごいな。
Hello? Yeah, okay, April. Padadan, yes. Yeah, because Prof. Siono would like to see your face too.
Yes, thank you.
Hey, don't be shy. Just
Don't be shy. Yes. I will waiting, yeah, until all of you can open your camera, and then we will start the screenshot. Okay.
時間かかんね、やっぱり。
Yes. The second slide also, I'm still waiting for you to open your camera.
どうやったっけ、これで4か。これか。
I will send this picture to Prof. Siono later.
うわー、すごい。みんな、チャンスがあるのかな。
Okay, guys, just open the camera, please.
時サイドは難しいんだよね。俺あれやってる人じゃないかな。
Okay, we will start.
視野に行ったらどうなんだ。
So let's start with the first slide, yeah? 1, 2, 3. Moving to the second slide. 1, 2, 3.
どうなってんだ。
Last slide. 1, 2, 3. Yeah, thank you very much. So thank you, Sensei.
Thank
I believe
you.
you still have another activities in your university. I hope we will see you again in another
See you
activities.
again.
Yeah,
Thank
see
you.
you. Have a good day,
Thank you so
Sensei.
much.
Bye
Have a
bye.
good day.
Thank you very much.
Bye bye.
Thank
Thank
you.
you.
Thank you, Prof.
Bye.
Yono.
Thank you.
Okay, thank you to the student as well. You can leave the Zoom. Thank you to all of the lecturers that have joined. Jamal, Putri, and others. Yeah, okay. I will close the Zoom. Assalamualaikum.